parallel parts, those are parallel. So I get 30. Multiply those, I get negative 21. So I end up with 9 joules. That force is doing 9 joules of work on whatever object that has that displacement. Questions up to here, because I'm now going to differentiate types of work. Okay. So I'm going to start out with total work. Total work is going to be the total force dot displacement. Hopefully not a shocking comment. If we will also get into conservative work, if it's conservative work, this will be the conservative force, total conservative force, and if it's non-conservative, this is non-conservative. But patience, we will get there. What is the total force equal to, according to Newton?
Does it include like opposite force? So is it like force double?
No. No, you're going overcomplicated right there. But generally, you're talking about the work being done on an object, and since from Newton's third law, we have forces in opposite directions, they're acting on different objects. So we're just looking at half that force component. Newton's second law, F equals. Yeah. Should not have been the silence there. At least I would hope not. Times displacement. What is acceleration times displacement? Flashback to chapter 2. What formula do we have that has acceleration times displacement?
So a formula has displacement and acceleration.
Yep.
This is off memory, but velocity final squared equals velocity initial squared plus 2a times displacement.
One thing I would nitpick on is speed squared.
Okay. Yeah.
All right, there we go. So therefore, acceleration times displacement is, so that would be Vf squared minus Vi squared divided by 2 is equal to A dot delta S. So this becomes mass times Vf squared minus Vi squared over 2. Now dividing by 2, generally, what I'm going to do is I need to distribute here. So I'm going to, instead of dividing by 2, I'm going to multiply by half. So 1/2 m, and then I have Vf squared minus Vi squared. Let's not forget the parentheses. And now distribute. I get 1/2 mv final squared minus 1/2 mv initial squared. Give you a moment to catch up or to ask questions before I talk about so what. Now the 1/2 mv squared comes twice, so that's so much to write. So let's come up with just a single letter to represent that. So what I'm going to do is I'm going to use a capital K. capital K to represent 1/2 mv squared. So therefore, this is equal to whatever K is, K final minus K initial, in other words, delta K. Yeah, you were here, you saw it. Work total is equal to delta K. I'm gonna write that up. That's an important enough equation. I'm gonna write it up over here. The total work done on an object is equal to this change in K. Why K? K obviously stands for something that's more than just random letters being thrown about. K is kinetic energy. This total work is equal to the change in kinetic energy. This is known as the work energy theorem. Personally, I'm not quite sure why they call it a theorem, because this equation is true because of the way they define work and the way they define kinetic energy. But I was not consulted. It is called the work energy theorem.
They're saying it should be work energy law.
Work energy definition. All right, so as you get further and further into physics, you find that a lot of the equations that we did are approximations. F equals ma turns out is actually a specific case of a more generalized formula, which we'll potentially, if I remember, get into in chapter 8. As you, and so on, I mean, all of our cake formulas, you'll find out, well, that's just a specific case where acceleration is equal to 0. Sorry, acceleration being constant, jerk is equal to 0. But if you're working on your Nobel Prize winning dissertation or your work, kinetic energy is 1/2 mv squared. So this is the one formula that I want you to be able to recite upon command. We're going to practice here in just a moment. So when I ask what's the formula for kinetic energy, the response is 1/2 mv squared. Don't embellish. Don't go 1/2 times the mass times the speed squared. 1/2 mv squared. 20 or so years from now, if I run across you in the street, and we look familiar to each other, so we've tried to figure out how we know each other, and then once I recognize that you are one of my students, I should be able to ask you what's the formula for kinetic energy, and you should be able to recite it. So, here we go. And I am serious. I want everyone's voice to be heard. What is the formula for kinetic energy?
1/2 mv squared.
A little bit out of sync there, almost the chorus of angels. However, not too bad. I will ask that at various times, and unison is going to be awesome. Questions up to here before we delve a little bit deeper. Now our formula over here, that the total work is equal to the total force times the displacement with a dot product. Suppose it's not the total work. Suppose I'm only looking at part of the work. Well, physicists have split force up into two different types. There is conservative forces and non-conservative. you're thinking the opposite of conservative should be liberal, then just remember, none of us were consulted. So, what is the difference between a conservative and a non-conservative force? Well, let's just think about the word conservative. It conserves something. What do you suspect conservative forces conserve?
Energy.
Yes. So if there are only conservative forces, energy will be conserved. Now, what are the conservative forces? There is a formal definition of it that really involves a line integral. So we will avoid that. And instead, what I'm going to give you here is a list of all the forces we have dealt with up till now that are conservative. Bless you. And again. Thank you. And done. We have only one conservative force that we have dealt with up till now. We will deal with one other one in this course. Ideal elastic force. We will officially get to that in chapter 16. However, we will deal with it sooner, but not expecting the complete understanding of what it is until we get to 16. Non-conservative forces, everything else. When you get into 152, electric force, magnetic force are also conservative. So friction, tension, other typically, and normal are all non-conservative. So let's take this concept over here. So if I have non-conservative work being done, that means energy is not conserved. So just sort of bring up there that if I have non-conservative work being done, then I'm going to have a change in energy. Not really deriving it, just sort of presenting it. By energy here, well, we need to talk about that. I have, this is my total energy, my total mechanical energy. Well, I've got kinetic. So there's got to be something else. So let's think through a problem here. I have a marker. What is its speed right now?
0.
Okay. If I let go, does the speed stay 0?
No.
Okay. So as it falls, my speed is increasing, therefore my kinetic energy increases. I'm assuming the mass of it doesn't change. Because kinetic energy, 1/2 mv squared, so as speed goes up, k goes up. What was the force causing it to fall?
Gravity.
Wait.
The weight.
Okay. Now I'm claiming that's a conservative force, so energy has to be conserved, but clearly it's gaining kinetic energy. So if it's gaining kinetic and energy is conserved, it has to be losing something else. So the powers that be decided to come up with potential energy. So we have kinetic energy and then we have potential energy. And as you would guess, the symbol that I will use for potential energy is a capital U. So if K is going up, U has to be going down, and vice versa. So this would have to be equal to the change in potential energy plus potential energy plus kinetic energy, because this is what I have. Which would just be the change in potential energy plus the change in kinetic energy. Well, I know change in kinetic energy is my total work. So now I have conservative, non-conservative work is equal to the change in potential energy plus my total work. I don't know why I put that in parentheses, but I guess it was the. Well, my total work has to be, it's the total, so it has to be made up of the sum of the different types of work. So that's the change in potential energy plus my non-conservative work plus my conservative work. That, so those are my only two choices. The sum of those has to be my total. Non-conservative work cancels out. Bringing potential energy to the other side, I'm left with my conservative work is equal to the negative change in potential energy. Even though the first one is called work energy theorem, those are the work energy relationships. And we will exploit that throughout, well, basically chapter 7 onwards. Questions up here? Now, if I ask you,
I was going to ask, when do you think you can get the recording of this uploaded?
I think sooner than I actually will do it. Yeah, because I just, I'm uploading like the past week's worth into YouTube now.
Okay.
So I hope to have, Tuesdays are packed, thinking by Wednesday morning. I was about to say something absolutely brilliant.
You should have come back to me.
Class is over.
No, that was not it. Okay. Perhaps not as brilliant as I was in. So if I were to ask you, what is the formula for potential energy? The correct response is, which one?
The opposite of kinetic energy.
Say it again?
The opposite of kinetic energy.
Not necessarily.
Negative.
And
kinetic
probably,
energy.
I mean, you could force it, but
Okay.
don't walk in with that assumption. And that would be change, if energy is conserved. So for every conservative force, and we do this in shorthand notation, for every conservative force, there exists a potential energy formula. For every conservative force, there exists potential energy. Write it out with words if you wish. So if I have a conservative force of weight, we will derive this at some point, but the potential energy formula is mgh plus a constant. If we're talking about the generalized gravitational force, so big G, mass 1, mass 2 over r squared, you get negative big G, mass 1, mass 2 over r plus a constant. If we're talking about the ideal elastic force, then you end up with 1/2 k delta x. And that's a lowercase k. This k right here is generally called the spring constant. And delta x is displacement from equilibrium. An example of the delta x there is, assuming it's just gonna hang there, there's some natural length it already has, so that would be equilibrium. As I extend it, delta x would be the distance from here, where it initially was, to wherever I or push it.
What is the h on the first equation?
The h, height. And height above what, we'll get to. Let's just zip through one example, and my plan is to actually derive this next time. object here, we'll start it at rest, the initial equals 0 meters per second. Started out with 50 meters above the ground, and I want to know when it is 10 meters above the ground, so it's gonna fall. What is the speed when it's 10 meters above the ground? So we start out with the force diagram. What are all the forces acting on this?
Wait,
Anything else? Pardon?
That's it.
Okay. Is that a conservative force or non-conservative force? Yes. So energy is conserved. So if I start out with, it doesn't matter which one I do, but I'll start out with this one right here. I have work, non-conservative is equal to the change in energy. I have no non-conservative work being done, so 0 is equal to E final minus E initial. And therefore my initial amount of energy is equal to the final amount of energy. At some point, we will skip some of those steps. But once we establish that energy is conserved, we have my total initial energy equals the total final. That is the essence of conservation laws of physics. My two types of energy, I have kinetic plus potential equals kinetic final plus potential final. Now we put in some formulas. I'm about to ask that question, so get ready. What's the formula for kinetic energy?
1/2 mv squared.
That was not as spectacular as the last time, but we'll get there. So 1/2 mv initial squared plus, and over here 1/2 mv final squared. And the formula for potential energy?
Which one?
Thank you. The one associated with weight.
MGH plus constant.
The constant's the same on both, so it can just cancel out. And typically, it's not written down, but I just want to emphasize the fact that there's a constant out there. Okay, now let's simplify it. Are any of these terms equal to 0?
The initial